going to talk about PCPs and something else, and again, it's going to be some analysis. So let me give you the background. This is a joint work with my student Kai, who's on the slides, and most of the slides are borrowed from him, so he's getting all of the credit for them. So let's start with something very basic, NP completeness. So 3SAT, we've seen it in several previous talks. I give you a 3CNF formula. I ask you, is it satisfiable or not? This is the classical decision problem of 3SAT. And we really like the 3SAT problem. It's very important because the Cook-Levin theorem tells us that it captures the essence of the class NP, which we care very much about. And once you know that 3SAT captures the class NP, you can start proving all of these NP completeness reductions and write thousands of papers, and people have done it. And this is the very celebrated theory of NP completeness. And this talk is getting started at the question of what happens when you talk about approximation problems and not just about decision problems. Well, in that case, we have an analog of the Cook-Levin theorem, which is called the PCP theorem. And here is one formulation of the PCP theorem. So it says that if I give you as input a 3CNF formula phi, it's NP hard to distinguish between the case that it is fully satisfiable and the case it is at most 0.99% satisfiable. So you have a gap of 1%. And just like in the Cook-Levin theorem, once you have this basic result, you can start doing a lot of reductions. This time it's a bit harder because you have to preserve gaps. But using it, you can prove a whole bunch of NP hardness results for approximation problems. But if you start with this very basic PCP result, you would often get relatively weak hardness results. For example, pick your favorite combinatorial optimization problem. So my favorite one is vertex cover. So you would be able to prove that it is NP hard to approximate something like vertex cover within factor very close to 1. Let's say 1 plus epsilon, where epsilon is some constant larger than 0. But you wouldn't be able to get very good constants using this basic BCP theorem. So, for example, for vertex cover, we know that there is a 2 approximation algorithm, and there is no way you are going to use this result to get close to 2. You need something stronger. So in what sense can you hope for a stronger theorem? Well, for once, you can hope for a bigger gap between the yes case and the no case. So now we're going to try to get a bigger gap. No, so I said something quite straightforward. If I just start from this result, not a better version of it, just from this result, and do basic elementary reductions, I'm not going to get very far.
Okay,
so
if you do take the 7/8 plus epsilon thing?
It's not going to help too much.
Yeah, that was my question.
Yeah.
So even if you're bettering the gap in the 3CNF case, you still, for vertex cover, won't get something.
Yeah. So, in actuality, what I'm going to do is I'm going to change the problem and the gap. But I was sort of trying to swipe under the rug the changing of the problem. You will see how it evaporates. Cool, thank you. So, so we need a bigger gap. And towards this end, we first of all have to reformulate 3SAT in a more general way. And this is what is known as the label cover view of PCP, and I'm just going to specialize it for 3SAT. And you can guess how it is formulated more generally. So I have my 3CNF formula. When you talk about label cover, there are 2 views. One of them is a 2-prover 1-round game, and one of them is a graph, and we're going to see both of them. So in the 2-prover 1-round game, the way to think about 3SAT is as follows. We have a verifier. The verifier is weak. There are 2 provers. They are strong. And the verifier is trying to use the provers to convince itself that phi is satisfiable. So the verifier is going to choose a clause CI at random. They're going to choose a variable from that clause at random. So the analogous thing in graphs is I have a bipartite graph. One of the sides is the clauses, one of the sides is the variables, and I have edges between a variable and a constraint that contains it. Okay, so that's the analog. Now the verifier sends the clause to one of the provers, the variable to the other prover, and they're expecting to an assignment, is expecting an assignment to the respective set of variables. So from prover 1, he's expecting an assignment to the 3 variables in CI, and from prover 2, he's expecting a single bit for xj. The analogous thing in the combinatorial view is what are the label sets of the variables. The label set of the left side is satisfying assignments to the clauses, and the labels to the right side are bit assignments. Cool. So now the verifier receives that, and the verifier accepts if and only if the 2 assignments agree on the shared variable xj. And in the combinatorial view, the constraint on an edge is that the label of CI agrees with the label of xj. Okay. So in this slide, we've transformed the 3-sat problem into something which is known as a label cover instance. And once we have this language, now we can try to think of how to amplify this business, how to get something with bigger gaps. Cool. Okay, so before that, let me just reformulate PCP. This is really a reformulation. So it says that if I give you such an instance, it's NPR to tell whether the value is 1, namely if you can satisfy all of the constraints, or you can make the verifier accept with probability 1, or the value is at most 0.9. Namely, you can satisfy at most 99% of the constraints, or make the verifier accept with probably at most 0.9. Okay, so we've reformulated the PCP theorem using 2-prover 1-round games, as well as label cover. Cool. Okay, so how do you amplify? So the point now is that using the formulation that we see, it's much more natural to see what part repetition is. So in the 2-prover 1-round game, the verifier now chooses k clauses independently, from each one of them is choosing one variable independently, sending all of the clauses to prover 1, all of the variables to prover 2, and accepting if they agree on the shared variables. In the combinatorial view, we can have a bipartite graph. One of them is k tuple of clauses, other side is k tuple of variables, and you have edges if there is inclusion. Labels are, again, assignments to the variables that there are, and the constraints are consistency. Okay. So our repetition theorem says that for the repeated instance that we have drawn here, if your original 3CNF formula phi was satisfiable, then the value of this thing is 1. This is easy. You just follow your nose and you design the strategy. And in the no case, if phi is at most 0.99% satisfiable, then the value of this thing is exponentially decaying in k, the number of repetitions. But this decay is not trivial. So there is an implicit constant here, CR, which is greater than 0. It is some constant. I don't know what it is. And it's small. Okay, so this thing decays to 0, but in some unclear way. Cool. But still, if we just care about large gap, we take large k, and we get a gap between 1 and something close to 0, and this is great. And if you start reductions from this problem, which is what often happens in the literature, you can start proving much better hardness of approximation results. So parallel repetition doesn't improve the soundness, but some of the other parameters become worse. So now we're going to complain about that. Cool. So first of all, what is the size of the instance, which is completely analogous to the size of the witness from yesterday. It's really the same, it's just different language. So the size goes to the power k. I mean, that's how it happens. And this was the topic, the size was the topic of yesterday, and we saw that you can improve it. So today we talk about something else. So now what we're going to complain about is about the following two parameters, the alphabet and the soundness. So the alphabet, well, I haven't defined it, but the alphabet size of an instance is the answer size. How many answers can a prover give me? So originally for the three-sat game, a clause is 3 variables. There are 7 satisfying assignments to a clause, so the alphabet size was 7. But if I repeat the game k times, now I get k clauses, so there are 7 to the k many options. So not only the size grows exponentially in k, but the alphabet also grows exponentially in k. And the soundness, it also goes down exponentially in k, but in somehow unclear way. So if you just stare at this alphabet and soundness and try to see what is the relation between them, you will see that currently they have a polynomial dependency between them. So if you note the alphabet size by q, you will see that the soundness is 1 over q to the power which is some small number, c. And the focus of the talk today would be what is the best possible trade-off you can hope for between your alphabet size and the soundness. So let's draw a line. So S, this is the soundness axis. And we saw that it's possible to achieve soundness, which is 1 over q to the c. We'll see some constant. And I claim that the soundness barrier is at 1 over q. Namely, if you have a label cover instance with alphabet size q, you're never going to prove NP-hardness with soundness less than 1 over q. Because if the provers just answer randomly with probability 1 over q, they're going to win. So this is as good as it can get. But still, there is a gap between 1 over q and 1 over q to some small power, and would like to know what the answer is. So what do? Do you try to construct better algorithms than the ones that just sample randomly an answer, or do you try to do better PCPs? So this is the range, and the first kind of solid improvement over this black box application of PCP plus parallel repetition was achieved by Kot and Safra, who gave some reasonable constant c. They proved that you can get soundness, which is 1 over q to the 1 over 6. Yeah, so the size of the proof is polynomial. Yeah. So then this was improved by Xiao and Chan, who got soundness, which is roughly 1 over square root of q. So I'm omitting some logarithmic factors. You'll have to forgive me about that. And we'll talk about it. There is some sort of bottleneck for some techniques that lie at this quadratic point. We'll see it. And what I'm going to tell you about today is how to get almost all the way to soundness, which is 1 over q, and we'll get to soundness, which is 1 over q to the minus 1 minus little of 1. So here is the more precise version of our main result. So we showed that for every epsilon larger than 0, if you take q large enough, if I give you an instance of label cover with alphabet size q, it's NPR to tell whether the value of it is at least 1 minus epsilon, or at most 1 over q to the 1 minus epsilon. Exactly, that's the point of this, of this more precise formulation. I really want to stress it that in this result, and also in the previous two results that improve upon this PCP plus PR, the value in the yes case is not 1, but rather close to 1. And I'll mention it in the end of the talk, but for perfect completeness problem, well, basically, we don't know how to improve the most naive thing that I showed earlier. And I think that it would be very nice if this can be done. But as you will see, there are some technical barriers that at least are inherent for the approach of this work and for Cotton Safra, and also for Chan, actually. So yeah, so that's a very interesting problem. But besides that, I want to mention one other fact about this result. So you can ask what is the runtime or what is the size of the reduction as a function of Q. And I want to comment that the size of this reduction is actually n to the Q, which is relatively mild. And this is important for one of our applications. Okay, cool. So let's see some applications. So as I said, the first one is just the result itself. It gets basically the optimal trade-off between the alphabet size and the soundness, and it improves upon these two works, which I already mentioned. The second result is the result where I mentioned that the mild size dependency on Q is important. And this is a result about approximation of quadratic programs. So a quadratic program over the cube is just a function like is on the board, summation aij xi xj over non-diagonal terms. And the problem is I give you such polynomial and I ask you to maximize it over the Boolean cube, which in this talk now is -1 to the n. So there is a fairly nice algorithm that gets an O of log n approximation based on semi-definite programming. And as far as hardness goes, so actually the motivation for this work of Cotton Safra was to get some lower bound for this problem, and they managed to show that it's a quasi-NP hard to approximate within factor log n to the 1/6. So quasi is because your reduction runs in quasi-polynomial time. Yeah. And as a direct corollary of our result, we get hardness of approximation within factor log n to the 1 minus little of 1. So now the second or the last application that I want to mention, I'll kind of half mention it. I will not even say what the result is, and honestly, I don't really remember. It just sort of applicativity to a bunch of connectivity problems. And here is an example of one of them. So this is a problem called rooted K connectivity, and it goes as follows. So your input is a weighted graph G, a vertex R, which I'm going to refer to as the root, and a set of vertices T, which are referred to as terminals. And my goal is to construct a subgraph G prime that has at least K vertex disjoint paths from the root to any terminal. And what I want to optimize is the weight of G prime. I want G prime which is as light as possible. So using this alphabet soundness trade-off, you can get fairly good hardness approximation results for this problem. And so this paper gives you a black box reduction from PCP, some results like that, and we just plug in our result and we get something. Again, it's not really important what exactly we get. I just want to sort of give the flavor of problems that are relevant, or at least some of them. You have a better hardness result. Yeah. For the rest of the talk, I'm going to tell you a little bit about some tools in the proof. And I will start by telling you at a very high level how do PCP constructions look like. And again, I'm not really going to do it. I'm just going to give you some very broad scheme and then focus on one component. So, just like any reduction, you have to start your reduction from some point. Like usually you start it from 3 sat. So we also have to start the reduction for some point. We call it the outer PCP. This is just a standard terminology. And in our case, we don't really use 3 sat, but we use some other problem called 3 linear. If you remember, I defined it in the first talk, but you don't have to remember. It's not going to appear. Okay, so we have some outer PCP thing. That's good. But usually, you know, the outer PCP, it has soundness, but it's nothing to write home about. It's some constant, just like 3-sat. So then you want to improve it, because you want a PCP with small soundness. So you apply parallel repetition. We have to apply some careful variant of it, but never mind that. And the side effect of parallel repetition, as we've already seen, is that the alphabet size grows. So it starts with being small, and it grows a little bit or a lot. So now we have this mismatch between the soundness and the alphabet, and now we want to bring the alphabet size back down. And this is done by a procedure called composition, which is the heart of almost all PCP constructions. And you do it with some other PCP, which is called inner PCP. Again, don't stress about terminology. But the effect of this composition step is that the alphabet size goes back down. So what's the gain? Like, we increased the alphabet, we decreased it, so what's the point? So the point is that when you increase the alphabet size, the soundness improved. And when you composed with the inner PCP, the alphabet size went down. So now you need to study the question of what happens to the soundness. And very high level, the soundness is inherited from the inner PCP. So as long as you can design some inner PCP which has good trade-off between its alphabet and its soundness, you are good to go. And this inner PCP, it's kind of coding theoretic object, something which is potentially much easier to construct than you know, some reduction from some unknown Turing machine. So the hope is that now that the problem is more combinatorial in nature, we can do it. So usually, so in the literature, sometimes these inner PCPs are called dictatorship tests or stuff like that. So that's what it boils down to, in theory. In practice, making this composition work is not like smooth sailing. It oftentimes doesn't work. And you need some compatibility between this outer and inner. But let's ignore it for this talk. Like, in this talk, I'm going to ignore this composition. And we're just going to focus on this inner PCP. That's going to be interesting enough. Let me maybe, sorry, this is completely off topic. But let me mention that this compatibility is really difficult. And if you know what is the Unigens conjecture, the main benefit of that is that it sort of gives you this compatibility for free. Like if your outer PCB is
Which conjecture?
Unigens. Yeah. It gives you this compatibility for free. And this is like half of why Unigens is so powerful, because you don't need to stress about this thing so much. It works more naturally. But again, put it aside, it's not relevant to this talk. Okay. So let's focus on constructing an inner PCP. So what is an inner PCP? So in reality, it's just some error correcting code with a local tester. And as we said, we care about the soundness of the PCB, which is just the soundness of the tester. So that's what we want. And if you remember these compatibility issues, in our case, it amounts to the code talking about equations which are linear and stuff like that, but don't stress about it. So when you take these compatibility things into mind, you really have only one candidate, which is the Hadamard code. So what is the Hadamard code? Well, the Hadamard code is a code where you encode a vector alpha in fq to the n using the truth table of the function f alpha, which is just the inner product function with alpha. Okay, so I have a vector alpha, I encode it using the truth table of the function alpha times x, where x ranges over all of fq to the n. So this is a nice code, it's very useful, we like it. It's a good error correcting code. So now we need to think about a local tester. I give you a function f from fq to the n to fq. I want to check whether it's some Hadamard code word or not. And the local test, really the only test that I know for this, is the classical BLR test, which proceeds as follows. You choose two vectors, x, y, in fq to the n randomly and uniformly, and you query f at the locations x, y, and x plus y. And then you check whether this equality holds. Okay. This is a really nice test. If f is an actual code word for some alpha, the test passes with probability 1. Great. And it's also easy to prove, at least if q is prime, that if the test passes with probability 1 over q plus a little bit, then your f is correlated with some actual code word. So great, right? We're done with the talk. Q is the alphabet size, 1 over q is the soundness of the test. Okay, we can go home now. Except that there is one issue. This test uses 3 queries. So we look at 3 locations. And if you want label cover, stuff like I said, you need 2 queries. So what do? So the idea is to try to shove 2 of these values into one symbol and hope for the best. So let's try this idea. So now we get to this more fancy thing, which is called plane versus point, line versus point. There are many things. We remember this function f alpha, but now we try to encode it differently. And these are classical ideas going back to ours in Sudan and to us at Safra. And the idea is as follows. Instead of encoding f alpha using only points, I'm going to encode it using points and higher dimensional objects. For example, I'm going to take points and planes. And I encourage you to think about it combinatorially. I have a bipartite graph. Left side is all of the planes in fq to the n. Right side is all of the points. And there is an edge if there is containment. So what is the plane versus point encoding of f alpha? Well, it's the most natural thing. It consists of a points table, which is just an assignment to the right side of the graph of values from fq, and a plane table, which to each plane assigns a linear function from the plane to fq. Now, what is the local test? Well, again, it's natural.
The planes are of which dimension?
Planes 2. So when I say plane, I just mean dimension 2. Yeah. So the plane versus point test is the test where you pick a plane P uniformly at random, you pick a point X from P uniformly, and then you check that the planes table, when evaluated at P, agrees with the points table at X. Just check consistency. So this is a test. It makes 2 queries now, which is what our goal was, because BLR made 3 queries. So now let's discuss the rest of the parameters. Soundness is still easy. It's going to be easy throughout the talk. It's always going to be 1. So if you are encoding some valid f alpha, test passes with probability 1. And the soundness, which in this case is harder, like it's not some one line, you can show that if you pass with probability 1 over q to some constant, let's say 1 over q to the 1 over 10, then these tables are correlated with some actual f alpha. Cool, so we have 2 queries, we have completeness, we have soundness, great. So this is the good, 2 queries, but the bad is the soundness and the alphabet that we got is not really what we're looking for. So first of all, before we talk about alphabet, let me just mention the soundness. So the soundness of this business can be at most 1 over q. Because again, random assignments get 1 over q. But the alphabet is actually q to the 3. So when I say planes, I actually meant affine planes, like not linear planes. So how many linear functions do you have in an affine plane? So there are 3 degrees of freedom. So q to the 3. So that's the alphabet size, q to the 3. So the alphabet size is q to the 3. Best possible soundness is 1 over q. So the very best, you'd get a cubic trade-off. And in actuality, even this is unknown. Like, we don't know this good of a soundness for the plane versus point test. It's actually an interesting open problem. So what to do? So, whenever in doubt, go higher. So let's go higher. So what does it mean? It means that instead of planes and points, we're going to take higher dimensional spaces. That's the only thing we can do. So now the graph that we're going to think about are R-dimensional linear subspaces in FQ to the n, and T-dimensional linear subspaces in FQ to the n. And you should think of T as smaller than R, but larger than 1. Now the R versus T encoding is just the natural thing. To each T space, I give a linear function, and to each R space, I give a linear function. So it's an even a bigger encoding. So that makes sense. And the test is also very natural, given what we've seen so far. You choose a T space uniformly. You choose R space that contains it uniformly. And then you check that the restriction of the function of the R space to the T space agrees with the T space. So let's count things. So first of all, the alphabet size of this thing is Q to the R, because there are Q to the R many linear functions on an R-dimensional space. That's good. The number of queries is still 2. And I claim, and we'll soon see it, that the best possible soundness you can hope for in this business is the minimum between Q to the minus T and Q to the T minus R. So we'll soon explain. But if you just stare at this and you try to optimize, you'll see that the best thing you can hope for is T is equal to R over 2, and this would get you a quadratic trade-off. And this is the quadratic trade-off that I mentioned earlier. Like, it doesn't matter how we pick the parameters, we're not going to pass this quadratic thing. Okay. Now I want to tell you why this best possible soundness is this minimum between these two things. So if I want to tell you that it's the minimum between two things, I need to tell you how do you achieve Q to the minus T and how do you achieve Q to T minus R. So Q to the minus T is easy. If you just choose all of the tables randomly, you'll see that it passes with probability Q to the minus T. And that's how life is. And Q to the T minus R is a bit more complicated. We'll see the construction. It will give us some ideas, but let's put it on the slide for now. And let me make the comment now that was already mentioned here, that this work of Cott and Safra actually really uses this recipe. They don't really discuss all of this business, but if you look at their paper, their encoding is take 6-dimensional spaces versus points. So R equals 6 and T equals 1, and they really utilize this Q to the minus. They show that this is actually what's happening. And it's really clean analysis. And
wait, Q to the minus T is good for us. That if we want to
sorry, Q to the T minus R. Sorry. Yeah, sorry. Thank you. Yeah. And Chen gets to this quadratic barrier, but it is not using this low-degree test. He's using something completely different. But still, for some reason, he's getting stuck exactly at the same place where this would get stuck. So how do you go past this quadratic thing? Like, why am I telling you all of that? So to get some insight, let's see the example that achieves Q to the T minus R, and this will give us some inspiration. Okay, so let's construct a counterexample. And by the way, for those of you that have been in Guy's talk, all of the business that I'm going to say from now until the end of the talk, most of it is going to, like, if you have the word dictator in mind, it will make some sense, in some generalized sense. But it's a bit hard to see from, like, at first sight. So we want to construct two tables, T1 and T2, that have nothing to do with an actual code word, But at the same time, they pass the test with probability q to the t minus r. Okay, so let's do some visuals. So this is still the graph that we have. It's still r-dimensional spaces versus t-dimensional spaces. And the way you construct such things is actually constructing another layer, let's say a layer of hyperplanes. So I'm going to take hyperplanes W1 to Wm. I'm going to choose the parameter m soon. And think of W1 to Wm as being generic, meaning let's say that I sample them uniformly. And for each one of these hyperplanes, I've also picked a linear function on them completely randomly. Okay, so these linear functions f1 to fm have nothing to do with each other. They're completely independent. Okay. So I want to use this business to construct an assignment for R spaces and T spaces. And the way I'm going to do that is in the natural way. So, this guy has an opinion about what should be going on in space. So he's just going to cast his opinion, like that. By that, I mean, I look at each R space, I look at the hyperplanes that contain it, I choose one of them at random and say, okay, I'm getting assigned by your function. For the T spaces, the same thing happens. For each T space, there may be hyperplanes that contain it. I take one of them randomly, and I choose them. I get assigned according to that function. That's the example. Now we need to analyze the example, and so I need to count the number of opinions. So for example, here's something that is clear. So I just need to count how many other opinions are there, how many second opinions does the T-space take. Yeah. So I need to choose M carefully. So let's see. Let's calculate a little bit. So actually, I'm going to take M to be constant times Q to the R. And the point of it is that if you look now at a typical R space, how many hyperplanes cover it? So a randomly chosen hyperplane covers it with probability Q to the minus R. So in expectation, M times Q to the minus R things cover it. So constantly many. Now, if you look at T-space, the number of things that cover it would be, by similar considerations, Q to the R minus T. So he has slightly more opinions, but not too many more. So now if you think about it, it means that the probability that they choose the same guy would be 1 over Q to the R minus T. Okay? And this is what gives you the passing probability of the test. I'm proving that there exists a choice of the W's and the F's where there is no global function, but the passing probability is good. Yeah, so I choose one of these opinions randomly.
That's perfect.
So that is the example. Okay, if you calculate the expected passing probability, you get exactly that. And if you think about it for a little bit, there is no global function here. There is no structure. The perfect completeness is lost at stage 0, where you start with 3 lin. But still, this example is not as bad as just choose completely randomly. I mean, there is some linear function in the picture. So it's not completely arbitrary. And you can hope for to salvage some structure from it. Maybe not the best, but some structure.
So you're going to play with the F's, that's how we should think of it?
I'm going to hope that this is the only thing you can do.
That
Okay.
would be
like maybe there is some other example. I don't know. Okay. So when I want to argue that if I have assignments that pass the test with good probability, then there is some non-random behavior happening combinatorially. And a way to see that is as follows. So suppose that I have these two tables, T1 and T2, and they pass the test with probability epsilon, which beats this random threshold, Q to the minus T. And I want to argue that they have to look like the example that we've just seen. And to see that, we pick a linear function f completely randomly, little f, and we define two sets of vertices. SL, which are all of the vertices on the left side, that agree with this little f that we defined. and SR, which are all of the T spaces that agree with this function little f. So these are two random sets which are correlated. And once you define things randomly, you can calculate expectations. So you can calculate the expected size of the sets. It's very easy. It's exactly what's written on the board. And you can actually calculate, or at least lower bound, the expected number of edges between SL and SR. So for each test, for each edge where the test passes, of which there are epsilon e many edges, the edge lies inside with probability q to the minus r. Because once the R space agrees with little f, that T space automatically agrees with the little f. So we can do this lower bound. But now you can think, I have two random looking sets of these densities. How many edges would I have expected to have between them? So if they're completely random, I would expect E times density many edges, which is this number. But the number that we got is much higher than that. So our SL and SR have substantially more than random looking edges. So this suggests that something should be happening there. And this is indeed the hook. This is where we start seeing that T1 and T2 cannot look completely random. They have to have some structure inside them. So what can we say about these sets? So it turns out that you can say something, and this is what you can say. I have a dagger there, which means that I'm lying, but something kind of like that is true. So you can basically prove that it looks like the example that I showed you. You can prove that, basically, it's not true again, but you can prove that there is some hyperplane and some linear function on that largely agrees with the tables. And this is referred to as non-standard decoding, because I only managed to decode something on a small hyperplane. And because it's non-standard, there are issues. First of all, how do you prove something like that? Because W is a very small set. How do you get it? And secondly, how do you use it? Because typically in PCP, you manage to get standard soundness, and then it's easier to work with, but this is more painful. Okay. So I'm not going to have time to tell you much about both of these things. So I'm going to tell you some things about some of them. Let's see what is the best thing to show. So this is the decoding theorem that we have. And one of the differences between this non-standard notion of soundness and standard notion of soundness is that you don't have least decoding bounds. Namely, usually when you manage to decode some closed code word to you, you also can prove that there are not too many code words that satisfy that. So you have a bounded list. In this case, there is no bound on the list. There could be many W's and many F's that would agree with your tables, just because each W covers a very small fraction of the space. So how do you handle that? So more precisely, here is a question. So we say that a pair of hyperplane function f is delta good if it delta agrees with the tables. And the question is, what happens when you have many, many tuples that are delta good? And sort of to get some intuition to what is supposed to be happening, you have many of them that are good. They're all correlated with the same table, T2. And because there are so many of them, they should be starting to self-correlate with each other, because T2 is the same thing. So if you have many things that self-correlate, you should be able to sort of glue them together to go even higher. So this is a lemma from a different context, from the context to do games, where we prove that if you have enough of these pairs, then you can actually find a function on the whole space that agrees with T2. But now the agreement is slightly worse. It's delta to the 12 and not delta. And in that context, it was like nice and we were happy. But in our case, it's unsatisfactory because our delta is the verge of triviality. It's just slightly higher than Q2 minus R. And delta to 12 is way beyond triviality. So we cannot afford that. So what we have to do is prove a stronger version of that. And this is indeed kind of the actually main technical component of this work. We managed to improve that lemma and show that actually you only lose a constant. Only delta over 5 is necessary. But the proof of that is significantly more complicated. Like you use stuff from direct product testing, you use the analysis of the plane versus point test, you use the global hyperconductivity that Guy mentioned, and some sunflower things, so it's quite a thing. But this is how you get beyond this list decoding issue. Cool. So I was hoping to tell you a little bit about how to prove it and talk about global hyperconductivity, but that's not going to happen. So I'm going to click a lot. And I'm just going to tell you that there is this thing called global hyperconductivity, which is related to what Guy was talking about. And it's pretty useful. I mean, originally it's from PCP, but now it has applications all over the place, number theory even. And specifically the result that we have to use, there is a recent result of Evra, Guy, and Noam. So that's mainly what I wanted to say, and now I'm going to click a bunch more. I was very optimistic. Okay. So let me conclude. No, so I was hoping to give some sense of what is global hyperconductivity and what it tells you, but instead I just clicked.
Can you put the slides available on the website?
Sure, yeah. Yeah, I could say things about dictators and this and that, but that's not going to happen now. Anyway, so we talked about alphabet Soundness trade-off and some applications, and I wanted to talk about global hyperconductivity, but some other day. So there are some open problems that are really interesting. So as I said, this perfect completeness business, if anybody can say anything about it, I'm all ears. There are some other problems, like is it relevant for sliding scale type things? I don't know. So there is this not very well-known conjecture by these people, which is something between sliding scale and 2-to-2 games. For a while I thought that maybe you can make progress on it, but I don't know. So I'm leaving it as a possibility. And generally this global hyperconductivity stuff is fairly useful, so try to use it. That's it. Thanks.